Okay, so I'm continuing about list management from the point we stopped the last video. We were talking about the expected length of search required for a given linked list. Okay, so here we have a linked list that requires one hop for A, 2 hops for B, 3 for C, and 4 for D. So if we use this definition of expectation, we get, and the probabilities that we had for our events, then we have that the expected value of L is equal to what? It's equal to 0.1 times 1 plus 0.2 times 2 plus 0.4 times 3 plus 0.3 times 4. Okay, and that's equal to, okay, so so this is equal to 0.1 plus 0.4 plus 1.2 plus 1.2, which gives you 2.9. Clearly, the fact that we have C and D here at the end of the list is costing us, right? Because if D here is 4 steps and it happens with probability 0.3, that costs us a lot. We would like to have things that are more probable in the beginning of the list. So what we would like is basically to order the list in the following way. First C, then D, then B, and then A. That's the best fixed ordering of the list, so that the expected length would be minimal. Okay, so we have expected length in this case is equal to 0.4 times 1 plus D is 0.3 times 2 plus 0.2 times 3 plus 0.1 times 4. Okay, so combining that's equal to 0.4 plus 0.6 plus 0.6 plus 0.4, which is equal to exactly 2. Okay, so 2 is significantly smaller than the 2.9 we got. Okay, so we have that the expected length is equal to the sum over I of P I times L I. Okay, where this is basically counting over all elements. Before we had the elements A, B, C, D, and this is the probability of element I, and this one is the position of element I in the list. Okay, so ideal, or optimal configuration is to do that if let's say that P1 is larger or equal to P2 larger or equal to P3 and so on, then we want L, the position, to be the same way. So we want L1 to be smaller than L2 to be smaller than L3, and so on. So basically it would be this in the first position, this second one second position, third position, and so on. Okay, so that's the ideal, but how can we achieve it? I mean, we can't assume in general that we know these probabilities ahead of time. However, we can approximate a PI using frequencies or empirical distribution, P hat I. Okay, and as I said before, P hat I becomes closer and closer to PI. So that suggests the following kind of algorithm. Algorithm is for each element keep count of number of occurrences and keep, that's the second thing, keep the elements sorted by decreasing counts. And you can easily realize that if you get one element in the sequence at a time, the corresponding count will just increase by 1, and so it's only a very limited range of where the element in the list should be moved. Okay, so this is pretty good, and converges to optimal. But requires counters. Okay. Okay, so we have optimal, which is sort elements in list from high to low probability. And then we have counts, which is the same, but instead of sort according to counts. So then we have methods that don't require counts, and the most well-known is move to front. Which means for whenever element is accessed, move it to be first in the list. And the other is move to front, and the other is never, so that's called swap. Whenever, okay, so in general we don't know fully how to characterize these, but we do know that MTF, so the length for MTF is smaller or equal to twice times opt, which is what we said above, -1.